Let's take a look at union and intersections. What's a join? We talked about this the other day. What's a join?
Or.
Yeah, it's an OR operation on two or more matrices. Very good. So if we OR those together, we will get this resulting matrix. And remember, the idea is we OR this with that to give us that. This with that to give us that, and so on down the line, right? That's the basic idea. What's a meet? It's an AND operation on two or more matrices, right? And same idea, if we ANDed those two matrices together, we would get that final matrix, assuming there are no math errors in there. And we AND that with that to give us this. We AND those two to give us this, and so on down the line, right? All the way across, up and down. We good with that? That's just a review definition from the other day. Well, we know this is an OR operation. We also know that it's the same as the union of two or more matrices. It's the same as a union. So in other words, the matrix of relation 1 ORed with the matrix of relation 2 is equal to the matrix that is the union of R1, relation 1, and relation 2. Make sense? So this finds the elements that are in either one of the relations or in both of the relations. A meet, we know it's an AND operation, but the other thing is it's the same as an intersection of two or more relations. So we're saying that to meet the matrix of relation 1 ANDed with the matrix of relation 2 is equal to a matrix that is the union, or the intersection, sorry, that is the intersection of relation 1 and relation 2. Got it? It finds the elements that are in both, right? Our Venn diagram, that's the centerpiece. So right now we have this join here at the top, that's an OR operation. At the bottom we have the AND operation. If we swap out the symbols, union and intersection, it's the same thing. Get the exact same thing. Questions about that simple idea there? This is some tricky stuff here. Compositive relations. All right, so let's take a look at the basic idea of what this, I literally wrote basic idea. I was not expecting that. I wrote it. Let A be the set 1, 2, and 3. Let B be the set 1, 2, and 3. Let C be the set 1, 2, and 3. These are three different sets, all right? I'm doing this to just sort of simplify it a little bit. Let R be a relation from A to B, where it has the pairing AB such that you end up with 1, 2, 1, 3, 2, 2, 3, 1, and 3, 2. What relation that is, how A relates to B, don't worry about it, but ultimately we got this final relation of the set AB, the set from A to B. That's the ordered pairs we ended up with. We're going to let S be a relation from B to C, where we end up with those ordered pairs. Okay? These are the premises we're starting with. We good? And again, keep in mind that little a is an element of big A, and little b is an element of B, and so forth. Okay? Now, using our terms that we know, domain and range, the domain in this first set here, do you guys understand that that's the domain? Right? It's coming from the domain there. Okay? It's not everything in the domain necessarily. In this case, it looks like it is, but it wouldn't necessarily be. But that's the domain. Where's the range?
Wouldn't the range also just be 1, 2, and 3, all the y values, right?
It's very good. The range is the y values. Right? The range is the y values. See that? Now, notice I highlighted the A and the B there in purple and green on the left. The A is representing the domain, and B is representing the range. Okay? On the bottom set, the domain, same thing. It's the B value in this case, right? And the range is the C value in this case. And again, I've highlighted the letters B and C in those colors. This is important. What relationship can you see with the domain and range of the first set and the domain and range of the second set? Do you see any connection there?
The range of the first one is the domain of the second one.
Very good. The range of the first set is the domain of the second set, right? B and B, right? Both of those are coming from B. Well, in the first relation, A to B, B is the range. Everything that's in B, the big B, is the range. Everything that comes out of there will be the range that ends up in that set. And then in the second set, S, the second relation S, from B to C, we're using B as the starting point, the domain. Okay? Does that make sense? We good on that? It's pretty quiet in here, just want to make sure, okay? So this idea of a composite, the composite of S and R will be a set of A, comma, C. This is kind of like the transitive thing, right? So, and I drew a little blue arrow there from the A to C to show you what we're looking for. So again, we're sort of walking through this intuitively, and then I'll show you, we'll kind of formalize it a little bit. But here's the basic pitch here. We're gonna move that stuff out of the way so we can see it now. And I'm spreading out those, I didn't change the values, I just spread them out so we have a little bit of space to play here. So first of all, here is the domain. Here's the range. What I'm looking for now in my second set is something that starts with a 2. And we've got 2 of them, right? This is much like what we do when we're looking at transitive property inside of a single set, right? Make sense? So now I'm looking at something that starts with a 2 because looking at the green circles here, the top row there, the 2B, I'm looking for a place where B is now starting down below, and then I'm going to look at the values next to that, those circled blue ones. So now the pair that would be in the composite of S and R would be 1, 1 and 1, 2. Do you see that transitive nature there? We good with that? Is everybody clear on what I'm saying there? Yeah. So let's back up a couple slides here. Think of the transitive property, right? So we're making a transitive connection between relation R and relation S. So in relation R, I've got a 1, 2. So now I'm looking for anything that starts with a 2 in my second set. Those two start with a 2, right? Now I'm looking at what's their C value, their second value. 1 and 2. So I need to, in my upcoming set, that's the composite of S and R, have a 1, 2 and a 1, 1. Just like the transitive property, right? It's exactly the same thing. So now I have 1, 1 and 1, 2. That's going to be part of the set, part of the composite set of S and R, right? All right. So now let's take a look at the next set here. And I have 1, 3, which means I'm looking for stuff that starts with a 3 in the second set, those green circles. And then that means I need to have a connection from 1, my red circle, to the number 2 and to the number 3. So I need a 1, 2 and a 1, 3. We already have a 1, 2, right? So I just need to add a 1, 3. Right? Look at the next set. Okay, look at the red circle, it's starting with 2. And then look at the green circle, the 2 next to it, which means I'm looking in the second set for anything that starts with a 2, starting with that green circle. And I need a transitive property from the red circle to those blue spots. Right? So I need a 2, 1 and a 2, 2. This is exactly the same thing as the transitive property, right? So 2, 1 and 2, 2. Let's move to the next set here. 3, 1, which means that green 1, I'm looking for anything in the second set that starts with a 1. And then I need a transitive property from that red 3 to those 3, 1 and 3, 2. Right? 3, 1 and 3, 2. The last set here, 3, 2, I'm starting with the 3, and it's going to 2, the green one, which means I'm needing to look in the bottom set for anything that starts with a 2. And you can see the green circles down there. That means I need to have a transitive property of a set 3, 1 and a set 3, 2. Those are ordered pair 3, 1, 3, 2. They're already there. Right? I don't have to add them again. Okay, we feel okay about that? So this is the final resulting set. That's the composite of S and R. Conceptually, we get the idea of what's happening there. We're making a new set that is the composite of the 2. And it's the way you make the composite is this transitive relationship between the 2 sets. Okay? So this is how we denote it. It's S with the little circle. I couldn't really find a character for that, so that's the closest thing I could find. But it's S with a little circle and an R. Okay? That's how it's noted. That's the composite of S and R. when you calculate it in a matrix, it's just the Boolean product of R and S. Now notice it's backwards from the original, right? The S little symbol R, and then you calculate it by doing the Boolean product of R and S. Because remember, Boolean product of R and S is different from the Boolean product of S and R, right? So it has to be specifically that. One way that I've heard people say it to help remember it is they pronounce this S after R. I've heard people say that. I don't know if that's technically correct, but that it will help you remember it. It's S after R, and what do we have here? Down below, when I calculate it, I end up with the S being after the R. Okay, it's R times S. That's how I calculate in a matrix. To the whiteboards. All right, we've all had a chance to look at these and calculate them. Let's take a look. So the composite of S and R for the first two matrices there at the top, remember it's just the Boolean product of what? R and S, yeah, very good, right? And then the second one will be the Boolean product of S and R, and then the last one again is Boolean product of R and S. We good on that idea? Okay, as long as you can calculate a Boolean product, which we've done multiple times at this point. Last time we did some, and today we did some. So as long as you can do that, you should be okay there. Just check your answers with what I got here, and it looks like at least the one I could see here got this correct. You guys good over there? Yep. Take a look at the second one. And again, if you're watching the video and you're not in the classroom doing this, and you missed any, go back and double check the sections in the video about calculating Boolean product, or the previous set of videos. Second set here, looks like you got that correct as well, at least over here. Did you guys get it down there? Yep. And then the last set looks good. Okay, we good? Think we understand it, right? So this is just another type of operation that you can do. And remember, when you're dealing with, if you're going into being like a hardcore programmer or software engineer, it's all about efficiency. It's all about making your code run faster, run more efficient. And how do you do that? Well, with creating good data structures and creating good algorithms to manipulate those data structures and process them and read them and do whatever you're going to do with them. And so part of that is being able to understand data in general, understanding structures in general. And 2420 spends its whole life analyzing algorithms, right? That's what all 2420 is about. But what is it analyzing? It's analyzing your algorithm that manages a data structure, a graph or a tree or some, a left-leaning red-black tree or whatever, different data structures. This is sort of hand in hand, and some of it's sort of foundational to the stuff you learn in that class. But this is all to help you understand how to model data and how to do manipulation and calculations on it, right? Any questions about this idea? We're going to move to kind of a new topic here. It's still representing matrices, but it's using directed graphs, right? 2420 folks, raise your hand again. Who's planning on taking it, the rest of you, hopefully? You guys gonna take it?
We took it.
You already, well, your hand didn't go up when I said 2420. I didn't see that, all right. So everybody's either already taken it or will take it, is that correct? Is anybody not in that category or are currently taking it? Good.
Yeah, but the people that don't show
The people that don't show,
up.
that need to know, that need it, yeah. So those who have taken it, what's a directed graph? You guys remember?
Graph that goes in a direction.
Yeah, there's two kinds of, basically, in very general terms, two categories: graphs that are directed and graphs that are undirected. Okay, a graph that's directed, it has a specific direction, right? An undirected graph, it goes both ways. It goes both. What does going both ways mean? We'll talk about that in a second. Okay, but all graphs will contain edges and vertices or vertexes, if you will. Or nodes is another name for them. They all contain edges and vertices. What's an edge? What's a vertice? Or what's a vertex? In this particular image here, the little circle, black circles, those are the nodes or the vertices. Each one of those is a vertex. Then the edge is the path from one to the other. Well, this path going from A to B, as you can see there, and from A to C, and then from B to C. That's a path. It's also an ordered pair, right? AB, AC, and BC. You see that? Okay, that's how you can represent them. So V is a set. And V, you can call it whatever you want, but it makes sense to call it V because it's of the vertices. And what's the set of the vertices? What's all your vertices, A, B, and C? It's a set, A, B, and C. So if I had a set A, B, and C, I could represent it like this with 3 little black dots. And then E is the set of all the edges. Well, the edges are the ordered pairs from one place to another. Because there's an arrow there, it's a specific direction. It's going from A to B. There is no B, comma A. If it were undirected, then there would not be an arrow there, it'd just be a straight line, and AB and BA would be part of the set. But we're dealing with directed graphs right now. Feel okay about this? So the edges are denoted as an ordered pair, as an ordered pairs. Nice typo there. No, who cares? I'm leaving it. I don't care. So edges are denoted as ordered pairs, right? A, comma, B. And A is what we call the initial vertex. And when I say A, I'm not talking about any specific one of these now. I'm talking about this A right here. We call that A in the ordered pair the initial vertex. It's the starting point, right? It's where you're going. And you're going from there to the terminal vertex, B, right? So look at this. We're going from here to here. Or with these actual values that match this actual graph here, we're going from A to B, from A to C, and from B to C, okay? The one on the left is the initial, the one on the right is the terminal. That sounds so terminal. It sounds so ominous. The terminal vertex. Also note that we're just, another way to look at this, we're just calling this set A like we were doing before. We have an A and a relation. I think this is an extra slide that's gonna, those values are gonna disappear in a second. That's probably a goof up in my slide here. But the purple there, this first set here, this is typically what we've looked at before when we're talking about maybe a set on itself, a relation on itself. We have A as our set. Well, now I'm calling the set V instead of A, right? That's all. And then the edges, that's the set of the relation. What's the relation? Well, it's the sets A, B, A, C, and B, C. This is the same stuff we've done before, right? And then notice that all those ordered pairs, A, B, are an element of the relation, and that should be little subscript A there, okay? Make sense? So a relation on A can be represented with a digraph. That's the basic idea, all right? So here's a couple examples. These are right out of your book. I just copied the images from the book and just stuck them in here. I tried to draw these in PowerPoint. It was a nightmare, so I gave up. So I didn't do it. Maybe if I wouldn't have done that, I would have been done at like 4 o'clock instead of 6 o'clock this morning. Anyway, so these are some examples of directed graphs. Let A, or our vertex, vertices, be the set A, B, C, and D, right? Let our relation, which is just the edges, be AB, AD, BB, BD, CA, CB, and DB. Do you see how, now let's make sure we understand every one of those, right? So AB, right, this is our first one. Well, that is from here to there. Notice how it's directing from A to B, right? We have AD as our next set. Notice again, it's pointing from A to D. That's our initial, that's our terminal. BB, this is how you represent when it's a relation to its, when it's terminal and initial are the same thing, right? Okay. And then we have BD, which is like half here and half here. And it's, again, it's going from B to D. I'm not going to really be able to draw a diagonal box there, but it's this big center one here. I'm going to remove that. Okay. And then we have CA, which is going from C to A. Again, I'm not going to be able to draw a box there. CB, going from C up to B. And then DB, right? This is going the other direction. So notice this one, we have it going from BD and we have DB, right? It's going both directions. Okay, do we see the picture? Is that we understand how to represent it? This particular representation, if you've already taken 2420, I know you've used this, right? And then when you got into graphs and trees, this is the very representation. Hopefully now seeing some of this stuff, and if you weren't familiar with sets and relations and set theory and all this stuff, maybe this maybe clarifies what you were doing a little bit with that stuff at 2420, but this is sort of the foundation of that kind of stuff. All All right, so hopefully we're understanding that picture there. Next one, same thing that's happening. I'm not gonna read through all the pairs, but you can see there's a relation from 1 to 3 and 3 to 1. There's a couple of ones that are bidirectional, 2, 3, 3, 2. Notice there's no 1, 2, but there is a 2, 1, right? So looking at this, can you already kind of tell some properties? For example, is it symmetric? It's easy to quickly see that it's not symmetric. Why is that easy to see? Without even looking at the sets on the right. Right, like for example, this pair here, if that was the only pair we were looking at, 3, 2, 2, 3, and then 1, 3, 3, 1, that's symmetry right there, right? But we have this problem. We have a 2, 1, but we don't have a 1, 2. So if you have just a single directional line and you don't have it going back the other way, you're already not symmetric, right? It's pretty easy to spot. Take a look at this one. Again, this is just another they're all digraphs, directional graphs, that are just using nodes and edges. And you can use this to represent your set, okay? Here's another example that you might have. In this case, our set or our vertices are just A up there, A, B, C. And then what you're seeing here is all the relations. Now, is this one reflexive or irreflexive? It's reflexive, right? How do we see that? It's super quick to see that, right? Every one of these just has a relation to itself, right? Okay, good. Okay, this one. Now, this one, not symmetric, not reflexive, I should say, not reflexive, not irreflexive. Do we see why? Is it symmetric? Yeah, it is, right? Do we see why? Without even looking at the pairs on the right, you can quickly see that it is. When you see those loops back and forth from any point to any other point, then it's going to be symmetric, okay? Any questions about that basic idea?
So the last one was not irreflexive?
It is not irreflexive.
Why is that? Is it because there's not, A is not pointing to itself, and C is not pointing to itself?
No, irreflexive would be when none of them are pointing to themselves.
Oh, okay.
Right, no AA, no BB, no CC, no DD. The fact that we even have one, or in this case we have two, we have a BB and a DD, right? Here's the BB, and there's a DD. The fact that even one of those exists makes it no longer possible to be irreflexive. Good. Other questions? Yes, one last time. All right, let's take a look at the answers here. I think I just have them all on one slide here. The first one we have, it's only symmetric. Does anybody get something other than that? If not, if you've got a different answer, I want to have you defend your answer, because we know that it's possible that my slides are wrong. I've been wrong before, right? But I think we're all in agreement here. It's only symmetric, it's none of the other properties, at least none of the other ones that we're talking about in this class. The second one, none of them. It's not reflexive or irreflexive, nor symmetric, nor transitive, nor anti-symmetric. Does everybody see why that is? Make a list of all the ordered pairs here, right? There's an ordered pair, just real quick, I'm gonna do like two of them here. There's an ordered pair of A comma D, right? There's an ordered pair of A comma B. There's also an ordered pair of B comma B. There's DB and BD. Write down all the ordered pairs, then look at it for these properties in the sets, or dump it into a matrix and look at it to see and make sure you understand it. And then study these graphs and make sure you understand how you can see it on a graph, okay? Next ones. Also none. And it's pretty easy to see that it's neither symmetric, it's pretty easy to see reflexive or irreflexive. For the reflexive and irreflexive, you're looking for the loops, right? The loops on themselves. If you have all loops, reflexive. If you have no loops, irreflexive. If you have any combination of some and none, then it's neither of those two. That's easy. As far as symmetric goes, what do we look for symmetric? We look for a path from every point. Every point that has a path, it has a point going back to it. Look at the first one there. We quickly can see that there's an AC and a CA. When you have those big sort of double arrows on all the points to each other, it's easy to see it's symmetric. The moment you have a single arrow, you're not symmetric. As soon as there's a single arrow, it's not symmetric, okay? Transitive is a little harder to find. You just have to look for it and just kind of follow the paths and see, right? Okay? Next up. Also none. I think everybody got that correct as well. And then the last one, it is reflexive. Okay, did we all match? Okay, any questions?
Let's take one last look at each of these 5 properties here and how we can recognize them in a digraph. For reflexive, we're looking for very simply every single element of the set, or in other words, each node or each vertex, to be paired with itself. And the way we see that is with a loop. And so here is that loop right here. There's a loop there. And if we see that on every single edge, then we are set, and that is officially reflexive. Now, if we see like this situation here where there is one loop, but there's no other ones here, then this is neither reflexive nor irreflexive. The only way for it to be irreflexive is if there's absolutely no loops. So if this loop were not here, for example, and none of them were looped, then this actually would be irreflexive. At the moment, there are no examples of irreflexive on the screen here. But imagine if this B right here were not looped, then that would be, this top graph right here would be irreflexive. So reflexive is this one where they're all looping to each other, and irreflexive is where there are no loops to each other. Let's take a look at symmetry. Remember, for a digraph or a relation to be symmetric, what that means is every time there's an AB, there should be a BA. Every time there's a XY, there should be a YX. Every time there's a WF, there should be an FW, right? So the way you see that quickly in a digraph, it's very, very simple to spot. It's whenever you have these double arrows like this. You have an A going to B, and then you have a B going to A. Here we have an A going to C, and we also have the C going to A. So that's A, C, C, A. Same thing here with the D and the A. So in that situation, sorry about the scribbles everywhere, but in that situation, when you have loops from every element, so in other words, every connection is a loop like that, then it will be symmetric. So down here, we do have a loop from 1 to 4 and then 4 to 1, and we also have a 1, 3 and a 3, 1. But the problem here is we have a 2, 1, but not a 1, 2. So that makes this one not symmetric. So the only one on this page that's symmetric is this top left one here. All of the rest of these are not symmetric. They're not symmetric, and they're also not anti-symmetric. Remember that anti-symmetric is a situation where if there's an AB and a BA, then A is equal to B. Looking at each of our graphs here we have an AB and a BA, and A and B are not equal to each other. Remember that when you're dealing with a digraph, every little individual point is a different value. Let's take a look at this bottom one right here. This one's almost anti-symmetric, but not quite there. When it's anti-symmetric, take a look at this first pair here. We have AA. Now this is a situation where there's an AA and an AA, which is the reverse of AA, right? It's the same thing. And that's a scenario where both pairs exist, AA and AA, and they're equal to each other. So that, so far, just looking at A here, it would be anti-symmetric. But of course, you can't look at just one pair or one node. We have the same thing going on here with the B and with the C. So just looking at the A, the B, and the C, so far it seems like it's anti-symmetric. Where the problem comes in is right here. We have a BC and a CB, but B and C are not equal to each other. That's a problem. Now if either one of these lines were not here, so if I could sort of scribble this line out, and if we had this map right here, this would be anti-symmetric. The reason why is this would be vacuously anti-symmetric for these 3 lines here, because we're looking for a scenario where there's one ordered pair and then the reverse of that ordered pair, right? AB, then BA, and then those 2 values would have to equal each other. Well, we look at this and there is an AB from here to here, but there is no BA. So the hypothesis, or the P of our P therefore Q statement, the thing on the left of the arrow, doesn't even exist. Therefore, the thing on the right arrow doesn't matter. So it would be vacuously anti-symmetric. So to summarize these first 4 here, we'll talk about transitive in just a moment. With reflexive, you're looking for every node has a loop. All the nodes have a loop on themselves. Easy. For irreflexive, none of the nodes have a loop on themselves. Easy. For symmetric, every single vertex that goes to another vertex has to go in both directions. So in other words, you have these double arrow looking things from every point that's connected. That makes it symmetric. Anti-symmetric, you have no double arrows. You have only straight arrows. Then the last one here, transitive. Transitive it's pretty easy to spot. It's just a little, if you have a really complex graph, it can be a little bit messy. But the basic idea is this. Let's take this one right here, for example. There is a path from 2 to 1. And then there's also a path from 1 through this to 4. If that exists, then there must be a direct path from 2 to 4, and there is not. So because there is not, it's not transitive. So it's pretty easy to quickly spot something like that that's not transitive. To follow all of them to see if it is transitive can be a little bit messier, a little bit more time consuming. But you can quickly see if I can take an indirect route to a place, then there also must be a direct route to a place. So take a look at this situation here. We have an indirect path from 3 through 2 down to 4. That's an indirect path, and I should be drawing it along this arrow here that's pointing that way. But that's a 3 to 2 to 4. That's an indirect path. If there's an indirect path, there must be a direct path, which there is not. Therefore, it's not transitive. Now, this one over here looks like it might be at first glance. For example, we have an indirect path from A to B, and then from B to D, which means there must be a direct path from A to D, and there is. But we have to check every single possible scenario. And the one that's going to get us is a little bit tricky. Take a look at this spot here. There is a path from B to D. That's a path from D to B. And then there's another path from B back to D. That's an indirect path to itself, right? A direct path to itself would be a loop. But this is an indirect path to itself. From D to B, then from B to D. Well, in order for this to be transitive, there actually would have to be a direct path to itself. This loop on itself would have to exist, and it does not. So because we have this indirect path through B back to itself, but no path on itself, then that makes it not transitive. This particular screen we're looking at, there are no samples of a transitive digraph. So hopefully that clears things up a bit. It's very easy to use a digraph to look at your set, your relation, and see what properties that relation has. For reflexive, every node has a loop on itself. For irreflexive, none of the nodes have a loop on itself. For symmetric, every vertex that has a path to any other vertex must have a path going both directions. Like the top left corner one, that's very clearly a symmetric one. For anti-symmetric, every single vertex that has a path to another vertex cannot have a path going the other way. In other words, we're looking just for straight lines, so one direction. For every single path, it's only one direction. With symmetric, it's all paths are two directions. With anti-symmetric, all paths are single direction. And lastly, for transitive, if there's an indirect path from, say, point A to point X, then there must be a direct path from point A to point X. And that's it. As you can see, using a digraph can be very useful when looking at the properties of a relation. So now we have in our toolkit the ability to represent a relation in a set, just a set of ordered pairs, in a matrix, and in a digraph. And all three of those, you can look for any of these properties we have on the screen here on the bottom right corner. You can look for them in a matrix by looking at all the patterns we've talked about in the past. You can look for them directly with the ordered pairs and just sort of trace out the numbers and the values. And then you can look for them with a digraph by looking at these visualizations we just spoke of. This can be an extremely valuable tool as you move forward in your career and in your education to help you model and understand data.